Hello, friends. I would like to welcome all of you to this webinar, What to Capture When It Breaks, 16 Artifacts That Reveal Root Causes. And I'm Ram Lakshmanan. So I'm the architect of Ycrash Product Suite. So let's get started. Okay. So friends, in this webinar, we are going to be discussing about 16 artifacts that will help us to isolate production problems, let it be a performance problem or functional problem or any sort of problem. These artifacts will facilitate us to get to the root cause of what triggered the outage, right? See, first I'll talk about what are these 16 artifacts, and then I'll talk about how to source these artifacts, how to get these artifacts, right? Okay, let's get started. Friends, the first and the foremost important artifact in troubleshooting is application logs, right? This is the number one artifact that we all go to identify the root cause of the outages, right? So what to look in application logs? The application log has a very verbose content, very enormous content. So what to look? See, there are several things you can look, but I would like to point out three important things to look in your application logs. There could be more, but I want to highlight these three. Okay. First one is there are some, I'm talking this specific to Java-based applications. So in Java-based applications, you want to be watching out for these errors, like a stack overflow error, out of memory error, class format error. So these are some of the JVM errors that's triggered by the JVM when there is any JVM related problems. So you want to watch out for these errors. Besides that, your application may have its own set of exceptions or its own set of errors. You may also want to track them, right? And then the next one, what you want to be looking in the application logs is the time gap between the log lines, right? See, oftentimes we look at the log statement. Every log statement has a timestamp. If you notice, so here is a to log statement. You see, this statement was printed at 6:59:58, right? Almost like 1.5 minutes later, the next statement is getting printed. And if it is happening, if it's printed by the same thread, it means the thread is stuck somewhere. The thread didn't move. For the time it moved from the previous statement to the next statement, 1.5 minutes elapsed. It means there is something going on in between those two statements, which is which is causing some slowdown or hiccups in your application. So you want to watch out for that, right? Okay. Now, the next artifact that what you want to be looking at when it comes to troubleshooting is thread dumps. Friends, what is a thread dump? Friends, thread dump is nothing but a snapshot of all the threads that is running in your application, right? So it tells the thread dump gives you what is the code execution path of each thread in your application. Friends, the thread are like a blood system of your application, right? They're like a blood system of your application. So say if I go to a doctor or a general physician and report some health ailments, the number one thing he resolves to is he asks for blood samples, because any part of our body organ has a problem, let it be heart, lung, liver, kidney, any organ. If there is any anomaly going in there, it will be reflected in your blood levels as a change in the chemicals levels or on the pressure. It will be visible. So they take the thread dump to diagnose what's going on. Similarly, whenever there is any arbitrations in our production environment, let it be a backend slowdown or a garbage collection running repeatedly, or there is a deadlock or any issues, you will see an arbitrations or anomaly in your thread behavior. So with thread dump, we can diagnose most of the performance problems, right? So this is an important artifact what you want to be picking up and troubleshooting. So how does a thread dump looks like? How does a thread dump looks like? So friend, this is how a thread dump looks like. See, um, let's just walk through some of what are the anatomy of a thread dump? What goes into a thread dump? The very first element, what is printed in a thread dump is the timestamp at which the thread dump was taken, and the next is what type of JVM from which this information was captured. Whether it's a 62-bit JVM, 64-bit JVM, or 32-bit JVM, whether it's running on a server mode or a client mode, we get those information. And then the next important artifact is the thread details, right? See, each thread, say my application may have hundreds of threads. Each thread has one segment reported in the thread dump. So this segment gives us the stack trace or the code execution part of the thread, right? So that tells this. So let's look into the details of each segment, what it is. So look at this. This is how each thread segment looks like within a thread dump. So the very first element, what is printed there is name of the thread. What is the name of the thread? And then priority of the thread. The thread can have a priority from 1 to 10, 10 being the highest and 1 being the lowest. So when there's a CPU contention, a JVM requests the thread with the highest priority to get a given chance to be run. But of course, it's up to the discretion of the operating system to honor it or dishonor it, right? And then the third element is the thread ID. See, each thread has an ID, right? The name is what given by the developer and it can be duplicated. The developers can duplicate it. But thread ID is unique because it is given by the JVM. And what is NID is? NID stands for native ID. So it tells, see, at the end of the day, thread is an operating system resource, right? So operating system needs to keep track of all the threads. So it keeps track of it by its naming and identification convention. For that, it uses its native ID, right? And then the next is the thread state. A thread can be in 6 different states. One of the state is runnable. That means the thread is executing, right? And then the 7th one is basically the code execution path of the thread, right? It tells the thread started out on this line, and from here it progressed to the second line, and then it went on to this third line. And at the time of taking thread dump, it was executing this particular line, right? So this is all the information that is present in the thread dump, right? Nothing more, right? But with this, we can do miracles. We can troubleshoot various sort of production problems, right? So now I want to share with you a real case study, uh, which this is a real problem that was confronted by a very major financial institution in North America. So their application started to slow down, and it was a middleware platform, and it started to slow down. As people in the session, if a middleware slows down or if middleware has an outage, none of the lines of business will work. None of the channels will, the banking channels will work. The online banking, mobile banking, ATM, the branches, none of them will work. So middleware's availability has to be always high, 99.999%, right? So that was having a slowdown. The thread dump helped them to resolve that problem for them. So now let's review that thread dump, which was captured at the time when the middleware was having a problem. So now I'm going in. Okay. So friends, when you look into thread dumps, right, you can open the text editor and then you can look at it as well. You're most welcome to do that. But there are some patterns what you want to be applying so that you can quickly see what is root cause is going on, right? So see here is a fast thread is a thread dump analysis tool. It applies various patterns to identify whether there's any problems is going on in this application. See, okay. See, one of the pattern what it applies. See, there's multiple patterns. One of the pattern what it applies is all roads lead to Rome pattern. I'll tell you where to get all these pattern information, right? What does all roads lead to Rome means? Friends, when Roman Empire was at peak, right? They strategically, the Roman Empire, they laid out the roads so that it doesn't part any part of Europe where they start. Finally, it comes to Rome, the capital city, so that the trade and economy can flourish, right? So that's the architecture they laid out. Similarly, my friends, whenever there is any bottleneck in your application, the bottleneck, there can be various bottlenecks, right? Whenever there's any bottleneck in the application, what will happen is the multiple threads in your application, they will start to navigate and then they come and then they end up in the same method, in the same point of code where the bottleneck is there. So let's say there is a backend is slowing down. Let's say backend is slowing down. Then what will happen is, and it is a primary backend, let's say it's slowing down. It doesn't matter what type of transaction what type of transaction comes to your application. Let it be a sign-on request or a funds transfer request or list transaction history request or any report generation request. All these transactions are going to come. Finally, they're going to be stuck on the method which is going to make a backend call, right? Because the backend is slowing down, backend is having some issue. So what you want to do is when you take a thread dump, you want to see whether multiple threads are coming and ending up in a particular method. If that is the case, then you need to analyze that method, go deeper into that, right? That may be a source of bottleneck. The report. Here is a section of the report which does this for you automatically. Look at this. Here it says 46% of the threads in this application are ending up in this particular method. And the tool gives you a warning. It says 87 threads are stuck waiting for response from the Oracle database server. It can slow down the transactions. Review their stack trace. Now, when I click here, you can see it shows the stack trace of one of the thread. You can see it was running on a WebLogic server, and now it is progressing. It is going along. And finally, you can see it is making an Oracle database call, and then it is getting stuck on this method. It's trying to read the data from Oracle database, but since the Oracle system of record is having a problem or hiccup, it's not responding. So this thread got stuck. So let me click on some other thread. This is a different transaction which is processed, right? So this thread is also originating, progressing, and finally it is getting stuck in this Oracle. It's going through the Oracle database driver and getting stuck here. Right? See, this can be even more beautifully visualized in the flame graph. So this is a flame graph. What does it do is it consolidates your entire thread dump. A thread dump is a few megabyte file. If you open in text editor, you have to go through one thread at a time. But here is a flame graph, is a graphical visualization which is showing your entire thread dump as in one single view, right? You can see this is the flame graph. Look at this, my friends. What's happening? Here, how to read this is, say, look at this. Let me start here. Here, it says there is a WebLogic thread. There are 6 threads are here. They're coming through this tower. Maybe this is one of the transaction. It could be a sign-on request transaction. It is coming in. And now, as they progress, you see, it is going to this Oracle JDBC driver. They're finally getting stuck when they're trying to read the content. Similarly, let's look at a different tower. This is a different tower. It's also originating in WebLogic. It could be a different transaction. It could be a funds transfer request. So they're coming in. And now finally, when they're going through this Oracle JDBC driver, they're getting stuck in this file dispatcher driver. So look at this. The way to visualize this, these are kind of different river streams, right? Different type of transactions. Finally, they're coming up and they're ending up in the ocean. Similarly, they're all going and they're getting stuck on this Oracle system of record. So this is one pattern. All roads lead to Rome. Like this, there's multiple patterns, like say, for example, traffic jam pattern, RSI pattern, athlete pattern. There are multiple such patterns. So what you can do, here is one of the webinar we conducted in the past where we talk about various patterns that what you can apply to the thread dump to get to the root cause. So if time permits, you may want to catch up on this video link, right? Okay. So now progressing along, the next artifact, what you want to be using for troubleshooting is heap dump. See friends, heap dumps comes very handy when you run into memory leaks or when you confront out of memory error. What is heap dump? Friends, heap dump is basically an binary file, right? It's a bin file. It's a binary file which tells what are the objects which is there in memory, who is referencing those objects, what is that object hierarchy. So it gives all those information. So when there is an out of memory error, I need to identify what is the leaking object, who is keeping that object alive. To do those sort of diagnosis, you need heap dump. right? So how to analyze an heap dump? How to analyze a heap dump? See, friends, I will talk about how to capture these artifacts at the end of my slide. But now, let's say you have an heap dump, how to analyze it? Friends, you can use the tools like Eclipse Mat or ePiro. These kind of tools can analyze you heap dumps and present you the root cause. So here, I would like to show you how to do this with the ePiro. So ePiro is a tool which can analyze the heap dump. So I have a sample hprof file, heap dump file. I'm going to be analyzing it. I'm going to be analyzing and showing it to you. How to do the heap dump analysis quickly. So now what I'm doing is I'm uploading my heap dump file, right, which I captured. Now I'm uploading it here. Or it also has an option. So if you have a heap dump in some remote location, like an HTTP server or S3 bucket, you can give that endpoint. Or if you want to directly transmit the heap dump from a production servers to ePiro for analysis, it also exposes REST APIs. Because heap dump is a very cumbersome file, it's a very large file. Downloading it from a production server to a local machine and from here uploading it can all be tedious and time consuming. And also heap dump also contains sensitive information. So maybe we don't want to get it to your local laptops. Directly stream it from your production servers to ePiro for analysis. So here is that analysis report. It analyzed and it's presenting you the root cause analysis of what caused the memory leak. See, at the very top, it gives you it has algorithms to detect what is causing the memory leak and then presents that to you here. This is a very good indicator. It says there is this object called map manager. It is occupying 99% of memory and all these objects are accumulated in this hash map. It's giving you in a very good English, right? You want to focus on this problem statement, what is reported. But friends, how I go about troubleshooting memory leaks or out of memory, that's what I'm going to be sharing. This is a very simple technique and it works 100% of the time, right? See, there are multiple sections in the report, right? There's histogram, threads, duplicate, GC roots, there are several things. But what you want to be focusing on is this largest object section. So this section tells you what are the largest objects which is there in memory. Friends, almost all of the time, your largest object is what responsible for causing the memory leak in your application. Because when the object is leaking memory, all the objects starts to get accumulated on one umbrella object. And that tends to be the largest object in your JVM. So what you want to focus on, come to this largest object section and look for what are the largest object here. If you see, there is this object called map manager. This object is occupying like a 99.95% of memory. All of them are occupying 0.01% or that kind of a stuff. So this is the biggest object. So, okay, now my next step should be, okay, this is the biggest object, but what is accumulating in that object? What made it to grow so big? I want to understand. To do that, what you do, click on this more and then say outgoing references. So this tells what are all the objects that is building up in that application. We'll get to know. So now when I click on this, this tells this object, this map manager's children. What are the children of this map manager? So this is what, these children is what making him to grow so big in size. Now when I click here, here is a map manager. When I drill down, I get to see all its children. What are the children of map manager? This map manager has an object called hash map. If you see, this hash map size is almost the same size of this map manager, the parent. So now let me click on this hash map. See, hash map underlying as a table, right? That's how it's implemented. So if I open it, you can see this hash map has like a 1 million records. You see, it has 1 million records are there. It's a surprise. Oh, I never thought, oh, this hash map would have a million records. What are the content that is present? If I click here, then you can see the raw data. What is the raw data that is present here? Here's the key and it's a large string. I get to see these values, right? Okay, so now what I've identified, I find the largest object and what are its children, which is a very good information. But now my next step is, What is keeping this object alive in memory? What is preventing it from getting garbage collected? To do that, you come back to the previous tab, be in this largest object section, and click on the incoming references. So what are the object which is referencing this map manager and which is keeping it alive? So when I click here I see. So now I get to see, oh, this map manager is referenced by an object called object1. And who is referencing this object1? This object1 is referenced by another class called memory leak demo. So like this, I can walk through the hierarchy to see who is keeping it alive. With this information, we can get to the root cause of what is causing the memory leak. That's all it is, my friends. Very simple. So look at the largest object section, look at the outgoing references, and then look at the incoming references. You will be able to nail down the problem. Okay. So now let's keep moving forward. So now, if you want to a little bit go deeper, some of the common memory leaks in Java and how to fix them, how to do heap dump analysis. Here is a video clipping, video tutorial. You may watch it at your leisure time. Okay. So now, next one, friends. What is the next artifact? Next artifact is heap substitute. What is heap substitute? Friends, heap dump is a very large file. So its size, the heap dump file size is more or less going to be equivalent of your memory size of your Java application. So if your memory size is 10 GB, your heap dump file size will be 10 GB. That's the approximate equivalent count. So if it's a 10 GB file, capturing it from production, getting it to your local laptop, and then uploading to EPRO, even though if EPRO is available in the cloud, and also it's also available on the on-prem installation, you can have it running on your local laptop. But still, then you have to still upload and then do that. It's a little bit tedious. And other thing is, EPDUM contains very sensitive information as well. Like as we saw, it contains the raw data. What if your application process credit card numbers, social security numbers, all those information is going to be there in EPDUM. And also, in all these 16 artifacts that I'm going to be talking, EPDUMP is an intrusive artifact to capture. App logs, thread dump, all others that we're going to talk is non-intrusive and it does not add any overhead also. But EPDUMP pauses your application. It can pause for several seconds or sometimes even a few minutes to take the memory snapshot of memory and write it to disk. So I will not encourage capturing heap dump always. Out of the 16 artifacts, I will not encourage capturing heap dump always. Rather, what you can do, you can go for capturing heap substitute. Heap substitute is an lightweight alternative to heap dump. See, I want to take heap dump only if it's an out of memory error. Only when I want to dig into memory, if I know it's a memory problem, then I want to take heap dump. But most of the time, it may not be a memory problem. It may not be a memory leak. It may not be an out of memory error. In that case, I don't want to take heap dump. In that case, rather I want to use heap substitute. Heap substitute gives me a high-level overview of what are the objects which is there in memory, what is their count, and what is the size they occupy. And it does not add any overhead to capture. So how does a heap substitute look like? So here I have a sample to show you how a heap substitute looks. See friends, don't worry, how to get all these data, how to analyze that, I'm going to be talking at the end. See, this is a heap substitute report. Here you can see it tells, okay, these are all the objects. And this is how much the size they are occupying in terms of percentage, in terms of absolute value, and what is the count. So here I see like a 330,000 of abstract queued synchronized node is present. So this is good enough for me to give a sense of what are the objects which is there in memory, right? I don't have to capture heap dump. I'll capture heap dump only if it's an out of memory error. Okay. So now I'm coming back here. So the fifth artifact that I want to capture is garbage collection log. Friends, there can be several memory problems happening due to garbage collection, right? A garbage collection can pause for a very long duration, right? When a garbage collection runs, it stops your application. Sometimes garbage collection costs can pause can span for several seconds. We have some case studies to show where it's spanning for several minutes. We have such data also to show. And sometimes what can happen is garbage collection can run repeatedly. So even though it can take a couple of seconds, it can take 2 seconds. But what if it's running, garbage collection is running every 5 seconds, it is stopping for 2 seconds. That can happen, right? When that happens, your transaction will start to time out because when garbage collection run, your application pauses, your application freezes. All transaction requests that the health pings, health checks will fail. And any transaction that your application is processing may not get a response. So, and then there could be various garbage collection related issues can be going on in your application. To diagnose this, you absolutely need garbage collection log, right? So how does a garbage collection log looks like? So friend, this is how a garbage collection log looks like. It has a lot of numbers, what size it was before the GC event, what is it after, how much time it took. It has all these information, right? So I want to share with you a real case study. This is a problem. There were timeouts were happening on the transactions and the application was going unresponsive. At that time, the garbage collection law really helped to resolve the problem for this very large insurance company. So let's look into the real example of this data, right? Okay, it is loading. So look at this. The garbage collection analysis. Um, let's focus on the look at see this is the garbage collection behavior. See, this application has been running for 10 days. This is a 10 days of garbage collection log from that insurance company. You can see the red triangles indicate there's a full garbage collection cycle that is running. You can see how intensely it is running. Maybe what I will do, I will just zoom in a particular, let's just see what is the GC duration, how much each GC event took. Oh, you can see, let me zoom in for a 1 day. Okay, let me even zoom in even more further. Okay, I will zoom even more, right? So this will become a small sample of data. Look at this, my friends. Here, one full garbage collection event ran. It ran, look at this, it ran at 10:06 a.m. Right at 10:06 a.m. it ran and it stopped the JVM for 2 seconds. You see, it stopped the JVM for 2 seconds. Now, look at this. Another GC event, this GC event ran at 10:06. At 10:07, another GC event is running and it is once again stopping for 2 seconds. Now let me move here. At 10:08, another GC event is running and stopping for 2 seconds. So you can see it is stopping continuously, right? For every 2 seconds. So for every second, stopping for 2 seconds. So that means the transactions are going to time out and it's running so intensely. So this is an garbage collection problem. We are not, if we look at generally from outside, oh, see, application is slowing down. What is causing the slowness? We don't know. We'll only know when we get the garbage collection log. This is just one example. There can be several things you can uncover with the garbage collection log. So, so what was the fix? What they made? Look at this. Their young generation and old generation was allocated 2 GB and 6 GB. So totally 8 GB was allocated as their XMX. Because garbage collection was running so frequently, they're running so frequently because this memory was not sufficient for them. So what they did, they let's look at the solution now. After they made the fix, how does it look like? Okay, once they made the fix, look at this, my friend. Look at the intensity of the GC events. It has reduced so much. Look earlier, this is the before the fix, right? Look how intensely they were running. Look at the red triangles, how intense. Now, similarly, for the same 10-day period, but see how lighter it has become. So lighter. So now let's look into the garbage collection. I'm going to be zooming in for the same 1 day period. Let me zoom in. Look at this. Now a 2 second event ran, GC event ran at 12:18. And now 12:40, that is what? 22 minutes later, and another event is running. 2 seconds earlier, it was happening for every minute. Now what? 12:40, another 107. What it is also another 27 minutes later, another 2 second event is running. The reason for this reduction in the garbage collection event, which is happening, is because they increase their young generation and old generation size. They increased that XMX from 8 GB to 11.5 GB. Once it was done, then the rate at which the GC events were running dropped. Okay. So now let's move back. So far, we have discussed 5 artifacts. Now, the sixth artifact, that sixth and seventh, I'm clubbing it together. 2 other artifacts that you need is top and PS, the process status. So what is top, right? Several of us are familiar with the top command here, Linux command. Friends, when you issue the top command in Linux, this is what the output you're going to see, right? What information is present in this top command output, and why it is important, for troubleshooting? Friends, first of all, top gives you 3 important metrics. The first important metric, what it shows is, what are all the processes running on that device or on the container? What are the processes running on that container? And what is the CPU and memory consumption of each process in that container is? So here you can see there is one process which is consuming 199.1% CPU and 0.3% of memory. And there is another process running which is consuming 0.7% of CPU and 1% of memory. It gives you this kind of information. Why this is important, right? See, our APM tools are giving us the CPU and memory utilization of our process, which we need for sure. But think about a situation. What if in your container, there is a cron job running at midnight 12 a.m. and it's archiving something? What if that cron job takes a lot of CPU cycles? Then your application would have a CPU starvation. Or what if there is some other homegrown script is running and it is chewing up the memory? Then your application will have a memory contention, memory issues. Those things will not come to our visibility. So if we are able to see all the processes running, and if some processes are taking a lot of CPU cycles or memory cycles, then that is an area that we want to be focusing on. We want to pay attention. Whether this is legitimate to be run, or is it hurting my application performance? Those things we will be able to address. So this is the first important metric we get out of top, right? Friends, the second important metric, what we get here is CPU utilization, right? Wait, let me turn on my pointer. See, we get a CPU utilization. See, here this tells what is the, see, we think CPU has just one number. A lot of people know, but CPU is broken down by top. Like, what is the user CPU percentage? That means what is the CPU consumed by the application, by our applications. And there's another metric called system level CPU utilization. This means this tells what is CPU consumed by the kernel. Kernel needs CPU cycles. How much cycle the CPU consumed by the kernel? Sometimes kernel has some issues. And what if it has an abnormal CPU consumption? If we see here, if we see, it will be reported here. And friends, what is even mesmerizing is there is another metric called stolen CPU time. See, this top and all was implemented like 4 or 5 decades before, right? At that point, they have implemented the stolen CPU cycle, which is very relevant in this modern container world. Because if you're in a container environment, if your container orchestrator, if your container orchestrator is not, sometimes it may not give enough CPU cycles to your container. Rather, it can steal and give the CPU cycles to some other container, which is running on the same host. When that happens, the stolen CPU cycle will go up. It can happen, and it has happened. So how we are going to get those visibilities? Just by looking at this top, focusing on these CPU utilizations, we'll see what is the problem going on, right? And then the another metric, what is very helpful is load average. Friends, load average and all is a very vital metric. It's getting forgotten. See, what is this load average tells? Load average tells it's a number, it's a unit, it's a number which tells how busy is your container or how busy your server is. So the first number it says, the first number here it says, what is the 1 minute average? What is how busy the system is for last 1 minute? The second number tells how busy the system is for last 5 minutes. And the third number is for last 15 minutes, how busy it is. So this is just a number which tells how busy the system is, right? Friends, this metric helped to say a very major problem in my personal experience, right? So it was very fascinating. I want to share this real world experience, right? See, there is a very major cloud provider, very major cloud provider there. So they were helping, their professional service was helping a very large financial institution to migrate their workload, which was running on their on-prem data center, to their to this cloud infrastructure. It's a professional service of a cloud provider. They were working with a financial institution to port their application, which was running on-prem, to cloud. When they migrated to the cloud, in the cloud infrastructure was not giving the same performance characters as when it was running on the on-prem. The on-prem had a better performance delivery than the cloud. So they were looking everywhere, and then they stumbled upon my garbage collection talk in YouTube, and then they reached out to me. Can you check whether it's a garbage collection issue? So when we looked, this load average helped to save the day. It was very fascinating, right? What happened was in the cloud, when they moved, they had a glitch in the load balancing algorithm. So since they had a glitch in the load balancing algorithm, that load balancer in the cloud was routing more transaction to one particular instance of one particular JVM. Other JVMs didn't have that much traffic. So when we looked into the load average across all their cluster of JVM, just one JVM had this load average of 100 or 120. Other JVMs in the cluster, they had a load average of 2 or 3. Then we looked at it. Oh, why this is having such a high load average? Oh, then they started working back and say, oh, there is a glitch in the load balancing algorithm. So more traffic it is routed to one instance. So that's what was causing the issue. So these are all the metrics which was developed in I don't know 70s. It is helping us today. It will help us in the AI world as well, right? Okay. And then the next metric, what will be very quite helpful is the PS, the process status. See, friends, the top command gives me process ID, uh, what is that user which launched it, and here it tells what is that application. See, but what it does, it doesn't give us a full arguments with which this application was launched. Look at this. It just says only Java, Java. It just gives the initial few characters. With this, I wouldn't be able to make out what is that application is, what arguments with which is launched. I don't have that information. Rather, if we use the PS command, process data, it gives us a complete argument or the complete argument which was launched. So marrying the top with the process status gives us a very detailed information. Okay, these are the process and these are this which is launched. It gives a very comprehensive view, right? So I say top lows process status. It's a match made in heaven. Okay. Okay. Now, friends, we talked about 7 artifacts so far. Now I'm progressing. Friends, top dash h. Friends, we have used, several of us have used top command, but top command has one secret option. It's called as a top uppercase h minus p process ID. When you give this command, what it will output? It is a very secret but a very powerful option. When you give this, the top command will print all the threads that is running within this process and what is each thread CPU consumption. It gives you. The top command when you give, it gives all the processes running on the device and what is the CPU and memory consumption. When you say top dash h and minus p and give that process, it gives all the threads that is running within this process and what is the CPU and memory consumption. Friends, this one becomes very handy when I'm trying to troubleshoot CPU spikes. See, CPU can spike up. Today, most of our monitoring tools, they tell, hey, a CPU has spiked to 80, 90 percentage. That is a good information. I need to know. For sure, I need to know. But what is even more important for me to know is, I need to know the exact lines of code that is causing the CPU to spike, right? That can be achieved with this top dash h command with and thread dump. See, when I issue this top dash h, it tells me, okay, there's one thread within your application which has ID 31306. It has a CPU utilization of 69%. There's another thread which has 31307, which has 65% CPU. And another thread by ID 31308, which has 64% CPU. All other threads have 0% consumption. So I know these are the three threads which is consuming CPU. Now, my thread dump will carry the information what lines of code these threads are executing, right? We saw about thread dump earlier. What lines of code they're executing. Now, if I can marry these two data, I can exactly, precisely pinpoint what lines of code that is causing the CPU to spike. Look at this. For this, I've gotten a real world case study. So this was a CPU spike, which happened in a trading application in North America. So, trading applications, the response time has been milliseconds, right? So what would happen is few JVMs in their cluster would have a CPU spike up to 100%. Once it reaches to 100%, it will not come down. You have to go ahead and recycle. Once you recycle, the application may run fine for several hours. And then it once again spikes up to 100%, it will remain there. Or sometimes after restart, immediately also it may go up. We don't know. The behavior was very sporadic. At that time, the thread dump and top dash h help to save the data. See, let's look into that example. Let's look into that example. Look at this. The tooling, what does it do? The tooling marries the top dash h output and the thread dump and presents a section called CPU consumption by thread. Look what it does. So this CPU percentage of each thread consumption is coming from top dash h. This stack trace of what this thread is doing is coming from the thread dump. Marrying these two gives us the exact lines of code that is causing the CPU to spike. So now here we can see there's a thread called web content 18. It is consuming 60.9% of CPU. I'm clicking here. Here is a stack trace. You can see the thread started out at executing, and now it is saying it is executing this weak hash map.put. Here's the stack trace, the exact code execution path, and saying put. And this is causing 60.9% of CPU. How can I'm putting into hash map can cause 60.9% CPU? Let's look at another thread. Here's another thread, web container 40. It is having 26% CPU consumption. So now when I click here, it started out. It is also into the same hash map put. It is having 26% CPU. What's going on? See, friends, hash map is not a thread safe implementation. It is not a thread safe implementation. If multiple threads starts to get or put concurrently, the thread will start to go on an infinite loop. When thread starts going infinite loop, the CPU spikes up. So that's what was going on for them. Once they saw this, oh, they're using weak hash map, then they replaced with a concurrent hash map. That resolved the problem for them. Okay. So now I'm going forward. Okay. So friends, now let's talk about the ninth artifact, which is demessage. Friends, here we spoke about application logs, JVM, the thread dumps, all of them. Kernel also has a log. Kernel also has a log, and that log also plays an important role in troubleshooting, right? So I want to, it's always easy to explain with an example. Here is a real case study. Here's a real problem that happened in an application. So that application, they moved from um, from a traditional monolithic environment into a microservices architecture in AWS EBS service. That's what they migrated from monolithic architecture. They moved to AWS EBS service, a microservice architecture. So when they moved, intermittently they were getting 502 errors, HTTP 502 errors. They were not knowing what's going on. So here dmessage helped them to solve the problem. Dmessage gives us the kernel logs. So to understand this, we first need to understand the EBS architecture. EBS architecture is nothing fancy. It is very simple architecture. At the very forefront, it has an AWS Elastic Load Balancer. It distributes the traffic to EC2 instance. Each EC2 instance has an Nginx server. Behind an Nginx server, each Nginx server, there is an Apache Tomcat server running. This is where the actual microservice is running within Apache Tomcat. So intermittently, they were getting this HTTP 502 errors. They didn't know what's going on. But the clue here is it was originating from Nginx. The Nginx is the guy who is throwing the error, right? The problem was going on for a while. Intermittently, it used to come, and then the problem used to get fixed by itself. It goes away. Only few customer reported, oh, I got HTTP 50 errors. Few L checks will fail. It's not very pervasive. Randomly, it used to happen, and then it evaporates automatically. But this problem was going on for months. Dmessage helped them to rescue the situation. The dmessage prints the kernel logs. So friends, this is how that kernel log was looking for this application. You can see sometime here it says it's printing out of memory, kill the process, Java process, or sacrifice the child. Friends, what happens is kernel sometimes can kill your Java application. When there is a lack of RAM capacity, kernel would kill the Java application. When it kills, it's not printed anywhere other than this kernel log. So what was actually happening for them was, look at this, the request would come and load balance will send it to one of the Nginx server. Let's say this Nginx server got it. Now it's going to forward the request to Tomcat. Now when Tomcat is processing the request, what if kernel killed it? What if kernel killed that Java process? Then Nginx will not get the response within the timeout window. If it didn't get the response in the timeout window, it's going to throw 502 error. Okay, so now the question some of you may have, if Tomcat is down and Nginx respond 502 error, then any request that goes to this Nginx should be getting 502 errors, right? Why it was not, why the 502 error was not so pervasive? And how did it evaporates also? Some of you may have that question. Friends, the answer to that is, this EBS architecture has a self-healing mechanism. That is, what it does is, it sees, if it sees Tomcat is down, the EBS self-healing mechanism will restart it. Right? It will restart. So what would happen? Kernel saw, okay, there's a lack of memory, so it kills it. Now the EBS self-healing mechanism would restart. So now the Tomcat becomes alive. It started to take traffic. And then after a point when there's no lack of insufficient memory, kernel would kill. So then Tomcat goes on, you get 502 errors. And self-healing mechanism restarts. And Tomcat keeps going. So actually Tomcat was literally jumping up and down in production, just like a cat, right? So these kind of things we need dmessage, the kernel logs. Okay, that's the next metric, what we want to be looking at. I'm adding the netstat and ping. And there could be several issues related to network contentions. Right? Say, what is netstat? The netstat gives us all the connections that I'm making to my backend systems and all the connection that is originating from the front-end system to my server, to my container. It gives me that. Why this is needed, right? See, sometimes what if your front-end customer, the client application is not closing the connections. He keeps on opening the connections. And what if the backend system is not closing the connection? Then those connections will start to build up. We will not get those visibility. Or sometimes even if you're a developer in a new release, he forgets to close the connection. Then those connections will build up. Where we're going to get those visibilities? We're going to get it only from netstat because it tells us all the connections and their count and what state they are. Very vital artifact to diagnose network contingency issues. And the next artifact here is the ping. The ping, I can ping the host. That ping, what does it give me? It gives me a round trip time, right? From my host to go to google.com and come back. What is the time? 1.74 milliseconds. That's what it's taking. What if there is some network latency is going on, or there's a lot of rerouting is happening? We'll not get a visibility. But if we get this, we're going to see them right away given to us. Okay. And then friends, next I'm presenting a bunch of host level or a container level artifacts to what is going on at your container or the host, like VM stack. What are the kernel parameters which is cost? What is disk utilization? Right? Sometimes what is the lack of storage? If my application is able to read or write from the disk, I may have an issue. And the metadata information I'm referring to what kernel version it is running, what Java version my application is using. Those kind of information is needed, right? So this is the VM stat, kernel parameters, disk usage, right? And friends, besides all of them, besides all these artifacts, 15, the 16th one, I may need some more additional data than this, right? What are some configuration files I want to pick up of my application? There could be some other cases as well. So we need all these 16 artifacts. If we have all these artifacts, it becomes a lot easier for us to troubleshoot our production problems. So now let's go to the interesting part. How am I going to get these artifacts? How I can get it in an easy way, in a non-intrusive way? How can I get it? So friend, this is where we have this open source script. See friend, there is this open source script available in GitHub. The URL is here, right? You can go here. So when you trigger this script is going to capture all the 16 artifacts that we discussed so far. It's in Apache 2.0 license. There is no commercial thing to it. It's 100% open source. When you trigger it, it's going to capture all these 360-degree data and then bundle them as one single zip file, right? It's going to bundle them as one single zip file. And how does that zip file looks like? See, I have a sample zip file that I want to show to you. Yes. So you see, this is a zip file. See, I told by default, this script does not capture EPDUM. It does not capture EPDUM because it's intrusive data. If you want to capture EPDUM, you need to pass an additional flag, -ht flag to capture it. If you don't, it doesn't capture, it captures heap substitute and all other artifacts. So now this is how the zip file looks like. See, it's roughly a 300 KB file. You see, when I open it, it contains all these artifacts as text files, like my application log files. By default, it auto discovers your application log file, and it scrapes last 5,000 lines. If you want, you can configure it to capture more lines. Here's my thread dumps, metadata, netstat, ping, process status, top-h, VM. All these data is there. It's going to bundle them as one single zip file. Once you have the data, then troubleshooting can become easier. It can become easier. Friend, there are some few interesting key benefits of using this script. There are some key features of the script. First one is this script is platform agnostic. That is, it can run on Linux, Windows, Mac, Docker, Kubernetes, OpenShift, and we are also starting to support other platforms as well, right? And then next one is it does pristine data capture. Friends, some container distribution may not have netstat command. Some container distribution may not have top command. In that circumstance, how it's going to capture these data? Because in that circumstance, the script talks to the kernel directly and gets this information for you. And just to capture thread dump, it makes multiple attempts. If a JVM becomes very sick, it directly connects with JVM and takes the data. So details of what kind of depth it goes, you can find it in this link, right? And then extended data capturing. See, I told the 16th artifact is, okay, besides this 15, I may need some more additional data. It gives the capability to extend the script so that you can capture additional data as well. And also it has a lot of security and compliance features, right? Because this is a sensitive data you're getting from the production. You want to encrypt it. It does the encrypting. And EPTM contains sensitive information. You want to redact the information. It gives you those capabilities, right? And then the next one is one common question that we get is, what is the overhead the script adds? Friends, if you see all these 16 artifacts, EPTM is the intrusive artifact. But for EPTM, which it doesn't capture by default, all others are what it is. Application log is there in the disk. GC log is in the disk. All these Linux commands, the top, PS, etc. What is the overhead? It adds almost zero overhead. You cannot even measure what the overhead is. And then the last point is this entire script completes under 30 seconds and then it ends it there. That's it. Even after that, if you do a PS, you will not see any output. Okay. So friends, now, okay, so now once you have this data, once you have this data, you can do the analysis. But we also have a solution where you can do the analysis. Once you have this data, let's say I have this data, it's a zip file. What you can do, you can upload this zip file. Once you upload the zip file, there is this tooling. You can tag by a server or customer name and those kind of things, and you can make it search. So now if I upload, the tool is going to process all these 16 artifacts and analyze them, apply all those patterns, and then generate an root cause analysis report for you here. So here you can see what is my garbage collection behavior. Okay, here's my garbage collection. Here I get to see. What is my threads? How does it looks like? I can see. See, here is the processes report, right? We spoke about different CPU times. What are the different processes? And if anything goes beyond a limit, it can generate an alert. What is my storage? That it presents you all. And if anything goes by 80%, it can generate an alert. What is my network looking like? What are network connections? Oh, here there is so many connections going on, and they are in these states. Whatever we discuss, it catches, analyzes, and presents it to you. And it's also available, even the application logs, right? These are all the errors that is happening. What are the common errors? What are the time gap? Everything is presented for you here. And this is my kernel logs and the kernel parameters. You can see them all in one place. Okay, friends. So this comes handy when troubleshooting your application, or sometimes your application may run on a customer premise. It becomes even more compelling there because a customer they will only say, oh, your application has crashed or unresponsive. But if you ask them, oh, hello, customer, if you want to open a ticket with me, run this script. What are the output is giving, then open a ticket with me. If you say that now we have all the data, then the troubleshooting becomes a lot more easier than what we are doing now. Now we are asking him to give this data, get that log file, issue this command. All those communication hassles will go away, right? Okay, so friends, I would like to thank all of you for attending this webinar. Hopefully it was helpful, hopefully it was informative. We will connect with you in yet another webinar.